Swayam Prabha. Digital India. Educated India.
Hello everyone. In the last lecture, we have introduced a new algebraic structure called group. And we have seen certain properties and operations over that algebraic structure. We will see more such properties and variants of group algebraic structure in today's and the next lecture. To begin with, first let us try to relate two such group algebraic structures with one another. So, which we call as homomorphism. So, what do we mean by that? Suppose we have two groups G with binary operation O and another group which is H with the binary operations, respective binary operations star. We define a function f from this group to the other group in such a way that, and we call that this function is called group homomorphism if for every element AB belongs to G, we have an image of A in H and we have an image of B in H. So we can say we have f of A operation B, this element will be equal to f of A and the corresponding operation of H with f of B. So this is as per the definition that we establish the group homomorphism between two such groups G and H when this happens. Let us take an example to show that how do we define such group homomorphism. Suppose we try to declare a function f from the set of integers with respect to addition operation to the set of Z4 with respect to addition operation. So this is the equivalence class when we divide any integer with 4 and what is the remainder will fall in this class. Now this is indeed an homomorphism because you define this way that if x belongs to Z for every x, you define it as it belongs to the class this, which is basically, this class is basically nothing but all the elements that are of this form such that k belongs to integer. Now this is homomorphism because if you take two elements from this set and I perform any two element this operation, this will lead me to the corresponding fx plus y, which I know is basically fx plus fy. Sorry, this is which I know to be x plus y, which is basically fx plus fy. This plus is over Z4. So therefore it qualifies the properties of homomorphism, hence f we can say as a homomorphism from integer to Z4. With that, let us now try to define, so we can define such homomorphism with the other set as well. So we can easily say that in general we can define a function g in general from the set Z plus to the set with this where your n belongs to here. So this is indeed, so we can define such homomorphisms in general. So with that, let us try to see some of the properties that this homomorphism satisfies. So let's say we have defined a homomorphic function from G to O to H star. And we know that here, let's say EH is the identity element of the group H and EG is the identity element of group G. Now, we define the first property as follows, that EH is equal to f of Eg. How can we say that? Because both are groups, G and H, both are groups, and therefore we can say that this EH, if I operate over any element in H, it will give me back that element. Even if it is FEG, it will give me back this element. And this element is nothing but operating the same element with itself. So by left cancellation law, I can find that these two elements are equal. Sorry, by the right cancellation law, this two element cancels, which gives me this relation as an answer. The second property says f of A inverse is equal to FA inverse. What does it mean? It means that the inverse element of FA in H is FA inverse. So how do we prove that some element FA has A inverse as its inverse element? We take the operability of FA and FA inverse. What we found out due to group homomorphism, this is nothing but this, which means this is basically E of G, and I have just proved this is E of H. So this side holds. On the same way, we can also show that this with FA is equal to similarly as f of Eg is equal to EH. Therefore, by these two property, so by this and this two property, I can claim that my inverse is. Now, to have a more generic notion of it, we can say that f of A to the power n is, that is, n times I operate A over it, that is f of A. In H it is f of A whole to the power n. So you can easily prove it using mathematical induction, where we assume that for its particular n it should hold. So see, the base condition, if n equal to 1 it holds, fa equal to fa, nothing to prove there. For a particular n, if it holds for n plus 1, we try to see it in this way. This is nothing but A n O A. This is nothing but I can write it as A n star F A. By induction, I know this is F A to the power n star F A, which gives me the required result in terms of induction. This is n plus 1. Hence, I can prove this is true. Now, this can be also extended and shown for every integer this holds, and this is a simple extension. I leave it to you to think about this. So this is one of the primary three properties that we prove over a homomorphism. So since we are we have an understanding about subgroups, so there is a property 4 for homomorphism which involves the subgroups, which says that for all subgroups H of G, or rather for all subgroups S, because I have used H, so I will say for all subgroups S of G, Fs is a subgroup of H. See, this is pretty easy to prove, because the property of subgroups to hold, to prove this one as a subgroup, I need to prove that the closure holds and there is an inverse that holds. So let me have a proof for this. So what I will try to see that for, let's say for two elements A, B, any two elements A, B belongs to G, I have X equal to Fa belongs to H and Y equal to Fb belongs to H. Now, for any two such elements A and B, since I claim this way, so for any two elements, let us, for the sake of subgroups, since we started off with, let's say for any two elements S, this also holds, and this is basically FA, and this is basically the subset of, I would also write it as, this is the image of S, it belongs into, so I could write it this also. Now, if I say I have an operation X star Y, which means it is basically FA star FB, which is basically F of A O B due to homomorphism, is basically, see, A O B belongs to S, so this belongs to F of S. Hence, so this proves the closure property of two elements XY and the operation star in Fs. Now, so this is the first thing that we have proven. Now, the second thing that we would like to prove is the occurrence of inverse. Now, you know that I have proven a property like FA inverse is nothing but FA inverse. So with that, I can say that so see that this FA inverse belongs to Fs. So this inverse will also belongs to Fs. Since A inverse belongs to S, FA inverse belongs to Fs. So since this element inverse will also belongs to S. So this proves that the existence of inverse. So hence I can say that Fs, so therefore I can claim that Fs is a subgroup of H. So this way we can establish certain important properties of subgroups of a particular group under homomorphism. Now let us extend the definition of homomorphism a little bit, where we say that so we define something called isomorphism. Something is called group isomorphism. If I can say that if F that I define to be homomorphic operation from G function from GO to H star is a homomorphism, and if I say F is bijective, that means it is 1-to-1 plus onto as well. So then I can claim that this F is an isomorphism from this group to the other group. So to give you some of the examples of isomorphism, let us give some examples. So the first example we will take a group G, where I will take the elements of G as the complex elements, these four complex elements, and I take this under regular multiplication. Okay, so this is multiplication. And I also take my H as the group, let's say it is from Z4 with the addition. Now, I define a function f from this G with multiplication to my H, that is Z4 with addition, such that I have these four things happens when my f of 1 is equal to 0, f of minus 1 is equal to 2, f of I is equal to 1, and I define f of minus I is equal to 3. Now see, this is indeed this is, first of all, this function is 1-to-1 and onto, that is no doubt, because every element is mapped into 1 and only 1, and every element from the set Z4 has been covered. So it is 1-to-1 onto, that is of no doubt. So this is bijective. Now I have to just prove that it also satisfies the homomorphism principle. So you can check for arbitrarily all of the operations that happens here. So f into 1 star 1 is basically f of minus 1, which is my 2, which I can write it as 0 plus 2, which is basically f of 1 plus f of minus 1. You have to check all possibilities. I am just showing you two such possibilities, that it is indeed a homomorphism. So this is basically f of 1, which means this is basically 0, which I can also write as 1 plus 3, which means it is basically f of I plus f of minus I. So in this way I can define all other operations and then can say that this is an example of, this function is an example of an isomorphism. So this is how we call it, that f is an isomorphic function, or it is an isomorphism example. So very interestingly, if you try to look into this set of G, so what you find in this set of G is the fact that if you see the set of complex numbers that I have taken, and which forms a group anyway with multiplication, this group under multiplication, you see the elements, these elements under multiplication with itself can generate all other elements. So if I to the power 1 is I square is minus 1, I cube is minus I to the power 4 is 1. So this element generates every other elements. So does this one too. Minus I square is 1, minus I cube is minus I to the power 1 is minus I square is 1, minus I cube is I, and minus I to the power 4 is this one. So therefore I can see there are elements whose composition with itself multiple times in a cycle generates every other elements. So we say that this group is, we call it that this group is generated by I, and we write it in this way, or it is also generated by minus I. However, if you look at 1 and minus 1, 1 only generates itself, no other elements, and minus 1 generates two elements, 1 and minus 1. So 1 and minus 1 are not the generator for this group. So we call such kind of groups as cyclic groups, which is a new definition to our group. So we call these groups as cyclic groups, where for every element, so I can find, there exists an element I can find in the group belongs to G, such that for every element present in the group, that element I can represent using some of the compositions with itself, or let us try to write it in e to the power n, where n is from a set of integers. So its composition with itself will form a group. Now we call such groups as cyclic groups, and if we take some examples of cyclic groups, you have already seen one in the previous slide, so we can take some examples more. So one of the examples could be, if I take the group H is equal to Z4 with respect to plus. This is a cyclic group. Why? Which is the generator element here? The generator element you can find is 3 is one of the generator element, because 3 to the power 1 is 3. 3 square, which is 9, which is basically, 3 square is 3 plus 3, so 2 times, it is an addition operation. 3 plus 3 is 6, which is basically 2. 3 cube is 3 times addition is my operation, which is 9, which is basically 1. And 3 to the power 4 is 4 times, when I add it, it is basically nothing but 0. So this is one of my generator. So I say this is a cyclic group which is generated by the element 3. Similarly, under addition, it is also generated by the element 1 itself, because 4 times, so 1 time you add 1, it is 1, 2 times it is 2, 3 times it is 3, 4 times it is 0. Right? So 1 is also a generator of this group. Another example, the popular example that we usually follow in our groups, that is, if Zn plus star, if it is a ring, or in other words, we have taken at Z9 plus star as a ring. So all the units of the ring, so we call it as U9 under multiplication operation. So all the units of this forms a cyclic group. How? Which is the generator element you can find? You can find the generator is, one generator element of this group would be 2, because if you see 2 to the power 1, it generates 2 square. It is 4, so it generates 4. 2 cube is 8, so it generates 8. 2 to the power 4 is 16, so 7 is the remainder, so 7. 2 to the power 5, 32, which generates 5. And finally 2 to the power 6, which is 64, which is 1. So see, 6 elements of U9, everything is generated by 2. So hence we will call this is a cyclic group. And so my generators are, this group is generated by 2. And if you also consider 5 this element, every element is generated by 5. So these two are the generators of this group. This is an example of cyclic groups that we are studying. Since we also have the concept of subgroup, so let us also figure out that how do we define subgroups of a cyclic group. So if you revisit the example of U9, so what was basically your U9 is? U9 is nothing but this set, right? 1. So all the equivalence classes whose representatives are co-prime to 9. That's what the rings with unity where A inverse exists. All these things we have covered earlier. So these 6 elements comprises U9. Right? So now the question is that we are trying to define subgroups generated by some elements. So not every element generates everything. There are some elements, as we seen in the complex number case, -1 generate only 2 things. So therefore, I can see that the whole U9 gets generated by the element 2 and also by the element 5 that I have just seen. However, if you see the set of elements that are being generated by, say, 4, if you study those, you will find that the set of elements that are generated by 4 is 1, 4 and 7. If you study the set of elements that are generated by 8, you will see that the set of elements that are generated by 8 are 1 and 8. Which says that not every element is the generator for the whole set. And similarly, for 1 being an identity element, so any element, if it is an identity element, it can generate itself only, right? Because how many ways you operate it over the same element, it will only generate itself. So therefore, you can see there are subgroups generated by a group G. So we call this concept. So this particular concept leads us to define something which is known as subgroups generated by certain element X in a group G. Basically a subset of elements that can be cycled and found out from this X to the power i's. So why we define such thing? Because we will try to also prove certain properties over these subgroups as well. So similarly, if you take certain other examples, so this is one example that we do. The other example of the subgroup, if you try to figure out with that complex number case, so you will see that 1 minus 1 I minus I. This is a group, rather a cyclic group with multiplication operation. So essentially the whole group is being generated by I as well as it is being generated by minus I. The subgroups, if you see, the minus 1, it generates 1 and minus 1. And the identity element 1, it only generates 1. So these are the subgroups that are induced by the multiplication operation with this particular element by cycling it. So hence, I will say that the order of a group, if we again try to come back to our definition of how do we define order of group and extend it to order of cyclic groups, we can see that the order of cyclic group G is nothing but the number of elements that are generated by its generator, right? So order of any cyclic group or any subgroup, we will try to mention this by the number of elements by its generator. And since we say the number of elements that it could generate, obviously this could be finite element set and the order could be infinite, as we have already seen in our previous examples. And depending on this, we will try to prove certain properties relating to the order of a cyclic group. So let us now proceed with seeing that how order dictates some properties. So here we go. So first of all, let us try to see one thing, that when do we say that our order is finite and it's a cyclic group? That means I am saying that this is a cyclic group and this is finite. So one case would be that my element A is itself the identity element, which is a to the power 0, one element. So in that case, I will say that you have seen examples that with identity element, whatever you generate, the order would be 1. Now, as for the second purpose, we will try to see that if my A is finite and it is not equal to the identity element, when A not equal to the identity element, what can we say about the order? So since A is not equal to the identity element, therefore the elements that are generated by A, it will be of the form of this, and since we are saying it as a finite length, so this would be of the form of this, let's say till a to the power some value of k. Or we can, in short, we can tell that this is a to the power m, or rather we can say that this is equal to a to the power m such that m is integer and it's finite. Now when this is the case, then clearly one thing strikes in our mind, that first of all, let us see that any two of this finite element set can be equal or not. So first we will see that therefore if it is a finite set, we cannot go on generating all sets of elements along. So there must be some t where a to the power t will be a to the power s, because this set is finite. We cannot go on generating every set. And this is 1 less than equal to s less than t. This will happen. This implies that there is an element a to the power t minus s which is identity. So that means there is a span by after which if I say my s is 1, there is a span after which I will get the power t minus 1, a to the power t minus 1 as identity. Let us assume that smallest n such that a to the power n is equal to e. So therefore, now we have two cases in our hand. One thing is that we know since a to the power n is e, so the elements generated will be of this form: a square, a cube up to a to the power n, which is equal to e in our case. Now here inside it, this set, obviously the order of this set must be greater than equal to n. Why? Because if it is less than n, then if it is less than n, otherwise, if it is less than n, I have two elements, a to the power u should be equal to a to the power v for 1 less than equal to u less than v less than equal to n. And what does this reveal? This reveals me again that a to the power v minus u is equal to e, and you know that v minus u must be less than n because of this condition. So this says that some quantity less than n is equal to e, which basically this is a contradiction to our assumption n is minimal or the smallest, because we have chosen smallest n. So this cannot happen. Hence, at least we know that this would be, so this cannot be less than n. So we now know that this is greater than equal to n. Now what happens if it is greater than n? If this set is greater than n, then what happens? It means that I have a set of elements of a to the power I format somewhere beyond n. I have a k where the k is more than n, and I can represent k by division algorithm with quotient and remainder. And I say that my r is obviously greater than equal to 0 and less than n, and can have a k such that a to the power k, let us see what does it reveal. It will reveal a to the power qn plus r, which means a to the power n to the power q into a to the power r, which means this is a to the power n is our e, smallest n that we have already figured out. So this means that this is actually a to the power r. Now see, now if we have an element a to the power k also, it is a to the power r where your r is less than n. So any element beyond this limit is also a member of this. So there could not be more element than n. So it brings us to a very interesting observations that if I can say that the order, so I can say a order of this is a very interesting observation for order of cyclic groups. I can say order of the cyclic group generated by A is equal to, or rather we also write it in this way, is equal to n. When I can write a to the power n equal to e for smallest n. So in this cyclic group, where do I will find a to the power n equal to e? That smallest n is my order. So this is basically how do we determine the order of a cyclic group and define it. Now when we have defined such an order, so immediately the obvious question comes to our mind is this property. So the property of, let's say I have a cyclic group generated by A. So let's say A, so this is a particular property or theorem. A is cyclic group a to the power n is my E. Now I will try to see that if I have a k such that I have a to the power k is equal to E, then I will prove that n must divide k. So how do I prove about this one? Since you have already seen, so a k exists where this happens. So let's say by division algorithm. So by division I can assume that k is equal to some quotient into n plus r, where I can say 0 less than equal to r less than n. Now what happens to my a to the power k? My a to the power k now becomes a to the power qn plus r, which is a to the power n whole to the power q into a to the power r, which means it is e to the power q, because a to the power n is e in my group, a to the power r, which is nothing but equal to e into a to the power r, which is a to the power r. Now what does it contradicts? Again it contradicts the minimality, because r is less than n. So now see that because r is less than n, so if a to the power k is equal to e given to me is equal to a to the power r, then I contradict the minimal choice of n. Just now I proved, because the order is n, so a to the power n is equal to e, or in other words you can also say that I have this with my order of a is equal to n. So this contradicts the minimality of n again. So I can say that it is obviously the case that r must be 0. So my r has to be 0, which may imply that a to the power k is equal to a to the power qn, or rather the other way, if we say that k is equal to qn. So it implies that k is equal to qn, which means n is n divides k. So this proves the theory. So now with this proof, with this concepts of orders and the theorems of the order of a group is a to the power n equal to e, let us also move into some of the properties of cyclic group along with homomorphisms involved in it. So first let us take an example and then we will try to see the generic formula for it. So let us see the cyclic group with homomorphism, and let us take an example first. Again I define a function. So we know that this group is cyclic, the units of the ring with respect to multiplication, and I define it with this as a homomorphism. How do I define that this way? That for every element here of the form, so since un is cyclic, so u9 is cyclic, so I know it is generated by the element 2, or also it is generated by the element 5. So now I define that, let's take 2 first. I define that it is 2 to the power 1 an element, and I define it whatever be the exponent from z6, I define it this. So essentially my function is f of 2 to the power I is equal to I. This is my homomorphism. So now this, and if you go on, 2 square is 2. So this is basically f of 2 to the power 1 is basically the element in u9 was the element 2. This is basically 2 square, so the element in U9 was 4. Similarly, f of 2 cube is equal to 3, the exponent. The element in F9, this was 8. So in this way, if we see the other 3 elements too, we will get that f of 2 to the power 4 is equal to 4. 16 means actually the element is 7. F of 2 to the power 5 is 5, and the element there is 32 means 5. And f of 2 to the power 6 is our this element is 6 in case of homomorphism because the exponent, and this is your 1 element. So what does this reveal? That now if you try to see the homomorphic property, you take any 2 to the power m and operate with 2 to the power n with multiplication. It results that f 2 to the power m plus n. Due to homomorphism, this is the exponent where you map into, so you map into this. And now this is nothing but in the set Z6, this is m plus n. And when we write m plus n in the set Z6, it is basically 2 to the power m plus f of 2 to the power n. So we have the homomorphism is defined. The homomorphism is defined. Now you can see this is also a function which is 1 to 1 on 2. So it's an isomorphism because for every 2 to the power I and 2 to the power I goes from I1 to 6. And for every of them individually we have 1 to 1 mapping to Z6. So therefore it is also isomorphism as well. So it brings us to a very interesting observations, and if you also verify it with the others, so I give it to you to verify. If you generate with the element 5. So you try to verify that this will still be, if I take it as 1 and so on, it will still be, I give it to you for you to verify that this will still again be an isomorphism, as well as this homomorphism is obviously due to the function. So this brings us to a very interesting observation, another observation. See that we could map a finite element set. So if you see here, we could map a finite element set into another finite Zn, right? So n element cyclic group I can map to Zn. So hence this theorem results. So we have this theorem that if G is cyclic group and we have, let's say there are 2 conditions of this particular theorem. Condition 1 is the order of G. So G is a cyclic group, and if we say that the order of G is equal to infinite, then we could declare a isomorphism from this group to the set of integers with addition. The second thing says that if your G is finite, as we have seen an example, then we could have a particular isomorphism from this to Zn, where G is finite and this number is n, and which is obviously greater than 1, Zn plus. So here we can find f as an isomorphism. So the proof is pretty straightforward because here, because see that in case of infinite, so what you declared is your function to be as, since G is a cyclic group, therefore there is an element to the power k where every element can be generated with. So I declared this as k. So I am proving the first case. This has K which belongs to Z. See, for every iteration till infinity, I will have one element mapping. So this is an isomorphism. This is 1 to 1 and on to. So it's an isomorphism, and this is my homomorphic function. Verify that this is a 1 to 1 on to. Okay. And second case, for f an element, generator element a to the power k, I will just do that. It's an equivalence class k. So this equivalence class k will be inside in Zn. So this homomorphic function, as we have shown an example previously, is also a 1 to 1. So both of these functions are 1 to 1 and it's an on to function. And why this is a function? Because two different K1 and K2, if K1 not equal to K2, then they belong to two different classes, right? So if in the class K1 not equal to K2 happens, it is bound that a to the power K1 will not be equal to a to the power K2. Okay, so it's a function. So no single a to the power K is mapped into two different classes. So it's a function, and this is my homomorphism with these set of definitions. So it's an isomorphism. So with this, let us come to another interesting property of this cyclic group. You can see that cyclic groups are formed by the elements of a to the power I, where a is my generator. So if I now see that I will have a particular proposition saying that every cyclic group is abelian. This is pretty easy to figure out, right? Because since every cyclic group has a generator, suppose G is a cyclic group, so let us try to prove it. Suppose G is a cyclic group which is being generated by A. Okay. Now, this is a cyclic group, let's say under operation star, which is any binary operation. Now, what I say that this any element of G is of the form of a to the power m, and some other elements will be of the form of a to the power n. So this is basically, when we say that this is basically a to the power m plus n, which is I can also write as a to the power n plus n, and therefore this is a to the power n and a to the power n. So hence it is, so every cyclic group, this property proves that every cyclic group is commutative. So this is my commutative property. Now, is the reverse case true? Is the reverse case is also true? Is every abelian group cyclic? The answer is no. And since to have no answer going, you need to just show a counter example. So let us try to see a counter example of such a group. So we defined such a group of, let's say, 4 elements rather. So we define an abelian group of 4 elements where my group elements are identity and let's say A, B, C. And I have the group operations as defined as this. So let us just draw a table for that. So this is the operation that I will define with E, A, B, C, E, A, B, C. So basically this will be the same as the elements both way. And now I will try to define that this is A, B is E, and now I will try to define this is C, this is B, this becomes C, this becomes A, this becomes B, and this is A. Now see, this particular group that I have built is commutative. Why? Because you see A operated by B, you check any two element operation, A operated by B gives you C, which is the same as B operated by A, because I have made a symmetry here, right? But this is not abelian, this is not cyclic, because you cannot find any of the element spanning every other with this operation, because A operated over it one time, two times, three times does not provide every other elements. So we see that every time we see that, let's say this way, if we write that, if we see order of the element generated by E is 1, order of the element generated by A, order of the element generated by B, and order of the element generated by C, if you try to figure it, it will be 2. You see, there are only 2 elements that will be generated by A and B and C. So this is actually not cyclic, and it is the minimum number of elements with which it is abelian but not cyclic. It is called Klein's group of order 4. So this is the minimum. This is the minimum possibility that could happen with order 4, that the group is not abelian. We call it as Klein's group of order 4. So indeed it is abelian, but it is not cyclic. Let us move on to one of the last and important property of such kind of a groups. So this property says that every subgroup of a cyclic group is cyclic. See here, what we indeed found out is the fact that, see, every element produces a subgroup. Now, this example, if this group was cyclic, then every element would have produced a cyclic group. So if you see the previous two examples here, let us come. Yeah, so the subgroups that are produced by this group. So this, I need to prove now. Let's say this ring of unity is this one. I will try to prove that every subgroups like this one and this one must also be cyclic. So every subgroup produced from cyclic group is also cyclic. So this can be proven in the following way. So my theorem says, every subgroup of cyclic group is also cyclic. If you have understood the ordering proofs, then this proof is very straightforward to you. So let's say we have H is a subgroup of G. And let's say G is a cyclic group produced by A. So therefore all elements of G are of the form a to the power m, right? So let's say H have the minimal element T which belongs to H, where I assume that my T is the minimum that it belongs to H. So now my claim is that H is a subgroup that will be generated by this a to the power T. Now, in order to have contradictory argument, let us have an element B which is a to the power S, which does not belong to H, and it gets produced by a to the power t. So first of all, we since all the elements, so one of the thing that we will like to produce is a to the power t, all the elements it generates, it's a subset of H. Now, when this kind of a B element exists in a to the power as form of a to the power s, I can write a to the power s is nothing but s. So for this s, I assume that my s is greater than t, greater than equal to 1. So for such s, I can write it is a to the power qt plus r, where 0 less than equal to r less than t. Now, what does this imply? This implies that a to the power r is equal to, so this is a to the power t to the power q into a to the power r, if we take a to the power minus t in both sides. So a to the power t into, a to the power t to the power minus q. So therefore I could say a to the power r is, this is my b, so it will be a to the power t to the power minus q into a to the power s, which is a to the power t to the power minus q into b. Now see that I assume that this particular element, a to the power t minus to the power minus q into b, so I assume that this elements, so here just for a clarification, but I want to assume that this element belongs to H, but this element does not get produced by a to the power I, but still belongs to H. Now I have to prove this is cyclic, so such an occurrence is not possible. That's what I want to give. So I assume that there are smallest t for which so first smallest t a to the power t belongs to H. Now I will claim, my claim is that all elements in a to the power generated by a to the power t will be in H. So but for contradiction, I assume there is an element which is not generated by a to the power t but also in H. So since this belongs to H, this belongs to H, the overall thing also belongs to H. Now here, look at the value of R, which is less than t. So if a to the power r belongs to H where r is less than t, then it contradicts the minimal assumption, the minimality of t as an element, such that I get a to the power t to be the first element that belongs to H with the minimal t. Hence, there should not be, so this assumption, so the assumption that I make that I could generate something which is, I could not generate something which is present in H, this assumption is false. So everything can be generated, will be part of H, and hence H is also cyclic. So the subgroup H is also cyclic. This way I have proven it. Right? Okay. So let us now move to another interesting definition of definitions, like, which is called the cosets. So let's say, since we are dealing with, so here when we say subgroup of every cyclic group is cyclic, so we are dealing with subgroups. So let us say H is a subgroup of G. Now for all elements A belongs to G, if I define a set like this, AH is A followed by H such that the H belongs to H. So this set under multiplication operation, so G, it's a subgroup under my operation, let's say, is multiplicative. We call this as a left coset of H. We call this as a left coset of H in G. So we call this as a left coset of H in G. Similarly, we could also define H into A is equal to HA such that my H belongs to H. So this we can call this as the same way. So this is my right coset of H in G. And so this is what for the multiplicative thing. So now if I go for additive, groups, I can easily extend the definition by saying it is A plus H. As the same way I could write it as A plus H such that H belongs to H, and H plus A is equal to H plus A such that H belongs to H, and this is for all A in G. So again, this we call it as left coset, and this call it as right coset. So just the additive and the multiplicative thing I both have shown both to you. So this is how we define cosets. There are very fine properties of cosets, but to highlight one such property, let us first try to take a small example first. So let us take the set, the group G as Z12 with respect to plus, and let's take the group H, the subset of that group H as 0, 4 and 8. So now you can easily find that I could also write the, so since it's an additive subgroup, so I can write that 0 plus H. So when you do that, all the element remains the same. So it is basically 0, 4 and 8. This is same as writing 4 plus H. This is same as writing 8 plus H. Similarly, if you go and write this one, if you write 1 plus H, you will get the set of element as 1, 5 and this is 9. So this is same as writing it as 5 plus H, same as writing it as 9 plus H. Now I just leave it to you that there are other cases will be possible. So this is, you can see this is H itself. The other cases are 2 plus H, just go on writing those, 3 plus H. So all these are left cosets as per the definition of cosets are concerned. So all these are left cosets. Now an interesting observation is that you see that the element subset that we are forming for G is basically when we say H union 1 plus H union 2 plus H union 3 plus H, right? So this induces the set of all cosets induces what is known by a partition. Remember the partition when we declare functions, this is a partition of G. So it induces a partition. So we will try to prove and see each of the cosets, left cosets that is formed from the subgroup H are of disjoint in nature. So we will try to prove these properties soon. So our property says that, that if H is subgroup of G, which is, let us say, finite, then we will try to prove first that for all A, B belongs to G, I will prove that either I will have the number of elements in H will be equal to the number of elements here. The second I will try to prove, here I do not need actually the B. The second I will try to prove that for all AB belongs to G, AH intersection BH is null, or I have AH equal to BH. So to prove the first one is very, very simple. How we will go? See the set AH, how we defined it. We defined AH as this, right? Now, since we define AH for every H as this one, so this set is obviously, so therefore it follows from the fact that for every H I have a AH value. It follows from the fact that this set must be less than equal to this. Now, if it were just less than, is less than condition at all possible? It is not possible because, see, if it were less than, then I have some H1 and H2 for which both of them will be same. If I have AH less than H, now AH, all of them are part of G because H is a subgroup of G. Now if they are part of G through left cancellation, I will have H1 equal to H2, as H1, H2 and A all are part of G. So this, since I assumed H1 not equal to H2 for different elements, so this cannot be the case. Hence all of them points to this, the fact that I have these two sets as equal. Now going for the second proof, so this is the first one. So going for the second proof, as we usually do, we will assume that we will assume the fact that AH intersection BH not equal to 5. So if that is the case, which implies there is an element C which will belong to their intersection, I am assuming they are not equal to 5. So their intersection has one element at least. Now since their intersection has one element, so let us call that element, that if their intersection has one element, so let us call that element C as A of H1 is equal to B of H2, because it's an intersection, so this element has this for both format. So now let us say that for an X belongs to AH, it means X has the form AH for some element H in H. For some H belongs to the set, I have this form. So what does this form reveal? This form reveals the fact that what is A here? From this I can find A equal to B H2 H1 inverse. So therefore I can find A here as B H2 H1 inverse operated with H, which is equal to B into H2 H1 inverse H. See, all of them belongs to H. So this composition also belongs to H. So this belongs to B H set. So therefore I started off with AH, which pushed me to from X equal to AH also belongs to BH. So it implies, so now we can say that it implies AH is a subset of BH. The other way is equally, you can prove the other way, that you take an element Y belongs to BH, which means you have Y of the form B small h, and from here, the same way from this relation, you can derive that my B is equal to A H1 H2 inverse. So this will give you as A H1 H2 inverse into H, which is basically A H1 H2 inverse H, which is basically belongs to B, which belongs to AH. So this gives you the relation that if your Y belongs to BH, so BH is also a subset of AH. So hence with these two I can say that my AH should be equal to BH whenever I have a common element between them. So either this will be true, and assuming that this is not true, I can found that this is true. So this is how we can formulate this or prove this one. The final property of this proof, which is very interesting, and it is called Lagrange's theorem, which says that if G is a finite group of order n, so if G is a finite group of OG, that is order of G equal to n, and H is a subgroup of G with O of H equal to M, if these two are the case, then obviously M divides N. How do we prove that? So this is pretty tricky as well as interesting. Let us try to think in this manner. First of all, since H is a subgroup, if G is equal to H, we are done. So if G not equal to H, the other case, so otherwise, we have this G not equal to H, which means there is an element A which belongs to G but doesn't belongs to H, because H is a subset of G, so there must be an element that belongs to G and not belongs to H. Now let us try to construct, since A doesn't belongs to H, now let us try to construct that, therefore we can say that this will follow a set AH. If we construct, this will not be the same as H. So if it follows that this will not be the same as H, so that means that I can say my AH intersection H is null. So now if these two induces a partition of G, which means that now I can say from here, if my G is basically H or AH union H, then mod G, the order of G is nothing but 2 into the order of H. So if it induces a partition, otherwise, If this is not the case, then there must be an element B which belongs to G but doesn't belongs to this set. Now when this be the case, this belongs to G, doesn't belongs to this set. Now if you see that since this does not belongs to this set, so since B does not belongs to AH union H, so therefore I can say BH also does not, BH is also not equal to what we call as H. That is, BH intersection H is phi. Now if let's say G induces, again G is induced, so B, this is phi, and also B doesn't belong to H because this is an union, so this is also BH intersection H. So this means that the set H, BH and H are disjoint, and if now G becomes AH union BH union H, three disjoint sets, then I can see the length of G is nothing but 3 into H. If not, I again get a member C which belongs to G minus AH union BH union H, and this process will continue so on until, remember, G is finite. So therefore somewhere down the line I will end this process by saying that somewhere down the line it will be the case when at the end somewhere G must be equal to A1H union A2H union so on up to AKH. So it must be the case that somewhere down the line I can get a k element partition of G which inducing G, because it's a finite every time, otherwise I will repeat this process, which implies the length of G is k into the length of H. That means that the length of H is M and the length of G is N, so that means M divides N. So this is a very interesting theorem which is called as Lagrange's theorem, which has very interesting ramifications as well. So if you look at two such ramifications, so what we call as corollaries. So one corollary will say that every finite group of cyclic finite group, so if G is, and for all elements A belongs to G, the order of the elements that are generated by A, so the cyclic group that is generated by this elements divides, can say that this divides the number of elements G. The second corollary is pretty interesting to prove, is that every group of prime order is cyclic. So see that if you have a group of prime order, that means it should be only divisible by, so let us try to have a sketch of the proof. So if your group G is of prime order, so this is prime. Now you from this group, every subgroup of finite this group. So I can also say every finite group of prime order. So the subgroup that you generate must be, according to our Lagrange theorem, it must be the subgroup, number of elements must divide your prime. So therefore every subgroup must have one or p elements. One element is the identity, p elements means the whole group G. This means identity, and this means the whole group G itself. So it means that if you take any elements and generates its subgroup through cycle, it will generate the whole set of group. That means your whole group is cyclic if it is of prime order. So you think it a little bit, it is just an application, or which we say a direct extension of. So this is a direct extension of Lagrange's theorem that we can find out. So we have learned an interesting properties and observations over groups. We have seen what are cyclic groups are. We have formulated subgroups of cyclic groups, certain properties for them. We have seen how to define isomorphisms of among group structures and along with the subgroups. And finally, we ended up with what are called cosets, and we have seen the properties of cosets, which defines a partition over the original set if H is a subgroup of G and it defines a partition. And finally, with the Lagrange theorem, we can find out that every subgroup, the order or the number of elements in the subgroup divides the number of elements in the group. So, thank you.